Right, thanks everyone. So, yeah, as Melissa said at the beginning, the people lecturing are around at other times, but my plans have changed and I need to go to Townsville this afternoon, so I'm not around for very long, so I'd love to talk to anyone who has questions about my lecture, but be quick. And also, as Melissa said, you know, the great thing about the Witter School is that you've got the experts in the field talking about their area of expertise, except for this lecture. Where I just looked and the stuff, I actually don't work on any of this stuff, and the stuff I know something about is on lecture, it's slide like 29. But anyway, what I'm going to talk about is the emissions that are happening now, and we'll look at them by country, per capita and intensity. Intensity includes aspects of economic output. Then I'll talk about the current sinks, where the CO2 is going, how much is staying in the atmosphere, how much is going to the land, how much is going into the ocean. And then Steve alluded to this, and I will talk in a bit of detail about what the future holds for the sinks, including the ocean sink. And then I have one slide at the end that is from the reading, the Rockstrom paper, and that shows a path to decarbonisation of the economy to meet the Paris targets. Okay, so the first part of my talk is talking about the global carbon budget, emissions and where they're going. And these data I likely got from this website, the Global Carbon Project, which is a compilation of a bunch of data sources to track carbon in the atmosphere and where it's going. And so the website is great. There's a bunch of different material on there, and the data is also published as a citable data record, and that's the paper there. Okay, so to talk about emissions, this is what's currently happening. These are the fluxes. These are not the pools, they're the fluxes. So the ocean pool is actually incredibly large because of the dissolved inorganic carbon in the ocean, but this is showing the exchanges between the pools. So together, burning of fossil fuels and land use change is contributing about 38 gigatons of carbon, of CO2 to the atmosphere per year. And just a word about units. So for almost all of my talk, I'll be discussing emissions in sinks in terms of gigatons of CO2, which is 1 billion tonnes, which is the same as 10 to 15 grams, which is a petagram. Sometimes you see the data represented as not weight of CO2, but a weight of carbon. And because of the molecular weight of carbon dioxide, you basically just divide the number by about 4 to interchange them. Yes, and on that website, the Global Carbon website, you can actually download the data and presentations in either format, carbon or CO2. So those are the emissions, about 38 gigatons of carbon dioxide per year. And the three major sinks, the ocean is taking up about 10, and is taking up a bit more than 11, and a bit more than 16 is staying in the atmosphere. So ballpark figures change a bit over time. Atmosphere is keeping 45% of the CO2, the land is taking up about 30%, and the ocean is taking up about 25%. Alright, so this is how emissions have been tracking. So this is from fossil fuel and industry, over time. What do you first notice when you look at this plot? Just tell me just yell out one thing that you notice.
It's increasing.
It's increasing, that's correct. But what else is happening? Yeah, it's slowing down at the end. It seems to be plateauing a little bit. And right here, there's a little dip. Does anyone know what that is? The GSC, right on. Okay. So later in my talk, I'll talk a little bit about economics, and there's a definite impact to the economy on fossil fuel emissions, and that's, I guess, not surprising. So these are the data that are synthesised by the Global Carbon Project, and yes, in some sense, it does look like there's been a plateau, and they suggest that it might be a lingering effect of the GFC.
What's GFC?
Sorry, global financial crisis. Yes. Okay, so how are we tracking in terms of scenarios? So I guess most of you are familiar with this acronym, RCP, Representative Concentration Pathways. So these are just different scenarios for how emissions might increase into the future with varying levels of mitigation or other measures to reduce emissions or their accumulation in the atmosphere. So this one here, RCP 8.5, sometimes called business as usual or worst case scenarios. So, and actually as I was reading this, I guess there is a bit of debate about are those two terms equal. This might be the worst case scenario, but we, as we'll see in some slides that I showed later, it's not actually business as usual. There is mitigation or changes that are going on right now, so it's not really business as usual. But as you see, we're tracking that pretty well. And I mean, if you look closely, you can see a slight deviation in the last few years caused by the plateau. So yeah, this is the RCPs, and below the numbers is the amount of warming that's expected based on those scenarios. So yes, emissions are increasing, and they are at the upper limit of what's predicted. So now let's delve a little more deeply into the emissions by country. And so these are the emissions of the four emitters or groups of emitters. So you can see a massive increase in China here since about 2000. In terms of emissions, the USA is actually decreasing, as is Europe, and India is increasing. I'll show later that this increase here is also mirrored in the global emissions due to coal. So I take that to mean that a lot of this increase in China is due to coal-fired power plants. Does anyone know where Australia is on this plot? So this is gigatons of CO2 per year. Does anyone know where Australia's emissions lie? Sorry? Right there. It's about 0.3 or 0.4. But wait. Okay, so here's CO2 emissions per person, so per capita, so just emissions divided by population. And you see that the USA comes to the fore there because of their energy intensive use, I guess you'd like to call it. China doesn't show up as much as it did in the previous plot. So where is Australia on this plot? Right there. Just a little bit below the US. And so, you know, so this thing here is often cited by people who don't want to do anything as a reason why we shouldn't do anything, why Australia shouldn't bother. But maybe this is a reason why we should bother, to be good citizens. Okay, so we can also look at emissions in terms of the amount of emissions per, I guess it's just divided by GDP. So emissions divided by productivity, or how efficient the production is in that country relative to its fossil fuel emissions. And so you can see massive increases in efficiency, so decreases in emission per US dollar output happening in China, and decreases in almost every region as well. There are several reasons for this, and so chief among them actually, so I just flew in from China yesterday, and chief among them is their concerns about air pollution management. So there are lots of things that are contributing to this increasing efficiency, so decrease in emissions per GDP. So some efficiencies in the economy, so replacing small plants and economic restructuring, increasing renewables. But yeah, air pollution is a huge issue in China, and so by obviously trying to do something about it, they're changing the efficiency of their economy. Okay, so we can look at emissions also due to the different types or the equivalents due to different types of power production. So the units here are mega TOEs, so a TOE is tons of oil equivalent. And so you can see perhaps a little bit of a plateauing in coal use here. So this is how much energy is produced by the different power generation mechanisms. Oil increasing, gas increasing. Now if you look closely at the nuclear here, there's a small decrease there. Can anyone say what that might be from?
Fukushima.
Yeah, right. So after Fukushima, Japan and also Germany decreased their nuclear sector, basically. And you can also see, so Steve alluded to the exponential increase in renewables, and I mean, sure, it does look small compared to everything else. And in my last slide, I'll talk more about that, about how is this going to continue into the future? Is it the scenarios can talk about renewables in terms of their period for doubling, and so we'll look at that in the last slide that I showed from that Rockstrong paper. Okay, so then this slide, so we saw the GFC, global financial crisis, in 2008-9-ish in that previous plot, but this slide highlights a couple of other economic drivers of emissions in the past. And when I first looked at this slide, I thought these were supposed to be arrows pointing to when the particular event happened, but what they are is linear extrapolations of a few years to emphasise the decrease in emissions that happened because of each event. So here in the 70s is the oil crisis, we all remember that, right? Jimmy Carter. What about the movie Argo? Do you remember that? Right. So the hostages in Iran are around about here somewhere. The savings and loans crisis here. So we're into Reagan now. Now we're into the first Bush here, the collapse of the Soviet Union. So there's a massive impact on the economy of that area. The Asian financial crisis, not so much. And here's the global financial crisis. So a big dip in this particular year, but suggestions that this plateau here might be a continuing effect of the global financial crisis. Okay, so let's talk a bit more about the sinks. So as I said, the atmosphere is retaining about 45% of emissions, the land is taking up about 30%, and the ocean is taking up about 25%. So these are the CO2 emissions due to land use change, and in the same units of gigatons of CO2 per year. So sorry, this is still showing sources, but it does it's going to feed into the magnitude of the land sink as well. So we see that there's lower emissions due to land use change in the 2000s. And we see two enormous spikes in this record because of the Indonesian fires here and here. And they are both due to El Nino events. So El Nino events have an impact on the CO2 in the atmosphere that is more than 2 gigatons of CO2 per year. So finally, I get to talk about the ocean. So let's talk about what's happening in the tropical Pacific. So that contribution to CO2 because of the Indonesian fires is very similar to, but opposite to, what happens in the tropical Pacific during an El Nino event. So many of you, there's probably some of you in the room who work intimately on ENSO in climate models and data. So this is a schematic of the tropical Pacific. Here's Queensland, Papua New Guinea, Peru, North America here. So normally, or during a La Nina event, the trade winds blow along the equator, cause upwelling, and they pile up warm water in the Western Pacific, and there's significant convection in that area. During El Nino conditions, the trade winds relax or disappear completely. The thermocline relaxes, has huge impacts on the Peruvian fishery, and it also can lead to drought in Indonesia because of the migration of this convection into the tropical Pacific. Now, during normal or La Nina conditions, this upwelling along the equator brings cool water to the surface, and that cool water is also high in nutrients. There is elevated productivity along the tropical Pacific, and you can see it in satellite maps of chlorophyll concentration. But this is a classic iron-limited region, and so the productivity there is not as great as it would be compared to the available nutrients of nitrate and phosphate. There's too little iron that's upwelled in those waters, and so there's also a lot of, because it's deep water that's being upwelled, there's a lot of inorganic carbon. So there's a release of CO2 to the atmosphere that shows up in global maps. And so this is one of the famous Takahashi maps of the air sea flux of CO2, made up from this one from a couple million measurements of surface partial pressure of CO2. And anywhere where it's red or yellow, the ocean is a source of CO2 to the atmosphere, and anywhere where it's blue and purple, the ocean is taking up CO2 due to both the biological and the solubility pumps. So we can see that this upwelling along the tropical Pacific that is not accompanied by significant upwelling of iron leads to low productivity and a degassing of CO2 to the atmosphere that is about 3 gigatons of CO2 per year. So that's about 50% of the US contribution from fossil fuels. Now, during an El Nino event, when this upwelling gets a lot weaker or completely disappears, that flux of CO2 to the atmosphere is much reduced, or it's zero. And so that's roughly the same order of magnitude as this increase that we see of CO2 to the atmosphere from the effects in Indonesia. So it's often difficult to see, if you just look at like the Mauna Loa CO2 atmospheric measurements, it's often difficult to see an impact of an El Nino event, because there are processes that are compensating for each other, and these are two of them. Okay, so then looking at emissions from comparing land use change and the different fuel sources, you'll see that up until about the 1940s, land use change in the sort of tan colour here was a dominant, was a very large part of the emissions. After the 40s, oil from, I guess, people being able to afford cars, and coal emissions increased dramatically. And so here, this spike in coal from about 2000 onwards looks a lot like the spike that we see in the emissions from China. So they're probably the same thing. Okay, so yeah, let's talk a little bit more about the sinks and how they might be changing. So, of the sources, burning of fossil fuels and cement production accounts for 91% of the emissions, and 9% is from land use change. And that total amount is going to 3 places: 44% in the atmosphere, 31% into the terrestrial biosphere, and 26% into the ocean. And what I'm going to get to is how these sinks might change into the future, and what implications that has for mitigation strategies in the future. So here's a plot that compares the sources and sinks. So above the horizontal line we have the sources, so fossil fuels and cement production, and land use change in the tan colour there. So we see a couple of spikes in land use change here, and they're reflected in a reduction of the land sink to basically zero at these 2 points here, which are 2 large El Nino events. So what I'm actually a bit surprised by here is I always thought that the 1982-83 El Nino was, compared to 97-98, was the second strongest El Nino that had been observed. But that doesn't show up as significantly as the 87-88 El Nino here, which was somewhat less in magnitude for the compared to the 1982-83 El Nino, but I think there are other things. I think the duration of that El Nino might have been a little bit longer, and obviously had bigger impacts on the land sources. So the 87-88 El Nino and the 97-98 El Nino have huge impacts on the land sink here, and then we see these dips here in the ocean sink, but they're not really dips, they're just effects of the atmosphere and the land combined. So as we go into the future, and I'll talk about some of the reasons why, and then I'll show some summaries in the last slide, these things might change. Sorry, was there a question?
I was just wondering, are these series stacked?
Yes. Yeah.
Okay.
So this, if I stack you, this change here flows on to these, if you know what I mean. Yeah.
Oh, okay.
So this is, this number here is these ones added up.
Okay.
Yeah. Okay, so here's another, so here I just showed you what the total amount or the current amount of the sinks are, and here it shows how they're tracking with time. And the main point here is that to some extent the sinks are increasing as time goes on as well. So as the emissions increase, the amount accumulating in the atmosphere is increasing every year, but also the amount that's going into the atmosphere as the land and the ocean sinks is also increasing. So and then those spikes for the El Nino events, we see them again here. So this is the 87-88 El Nino event and the 97-98 El Nino, and also the 2015 El Nino show up as they weaken the land sink, and so they cause a spike in the atmospheric growth in CO2. All right, so now let's talk specifically about the ocean sink. So this is how the ocean sink is increasing over time. The black line is from the Global Carbon Project. These coloured lines here are from different data products, and then the blue lines are individual ocean models, and the black line is a synthesis of these different data sets. So like I said before, the ocean, as we emit more, the ocean is absorbing more, but it's a very difficult problem to understand how that might be changing into the future. All right, and then this just shows again, this is just another way of looking at the sources and the sinks. So from 1870 to 2015, this has been the change in the atmospheric the concentration. So now we're talking in concentration units, not in tonnes of CO2 or carbon. So in 1870, atmospheric CO2 was 288. Now it's 400. That's because of emissions from coal, oil, gas, cement production, and land use change. And then the land sink has taken up, so again these rough numbers that I gave you, the land sink has taken up about the equivalent of 77 parts per million, the ocean the equivalent of 74, and that's what gets us to, so the atmosphere sink is the difference between this number and this number. And these are the observations from Mauna Loa. So this is the measurements that have been made on top of the Big Island in Hawaii, started by Dave Keeling in the 50s. And so we see the increase here, and there's a seasonal cycle that is mostly due to the terrestrial biosphere in the northern hemisphere. If you were to have a similar record, and they do exist from the southern hemisphere, the wiggles due to the seasonal cycle are smaller because there's less land in the southern hemisphere, and the seasonal cycle contributes a lot to this seasonal variability. So as you can see, we're approaching 400, and 2016. So the data in the Global Carbon Project don't go all the way to 2016. So I just amended this text here to say that CO2 concentration stayed above. 2016 was the first year that concentration at Mauna Loa exceeded 400 parts per million for the whole year. And these are just, the different colours at different years, so it shows the seasonal cycle and the annual accumulation in parts per million in the atmosphere. Okay, so of the ocean sink, where is that CO2 going? And the answer is it goes into the ocean very efficiently where deep water is formed or where water is subducted. So we can calculate, at the surface, we can calculate the flux of CO2 between the ocean and the atmosphere by measuring the partial pressure of CO2 in the surface waters and then parameterising the gas transfer velocity as a function of wind speed. To measure the amount of carbon dioxide that's going into the ocean, we can make measurements. We make repeated measurements along long transects of the CO2 concentration. And because the ocean, in the deep ocean, the properties of the ocean don't change very much. So these, every 10 years or less, there's a transect that goes from Alaska down to Antarctica. There's another one in the Western Pacific that was done last year by the Australia's research vessel, the Investigator. So these repeated transects that along predetermined lines that happen every decade or more frequently show us how the ocean is changing. And we know we can partition out the CO2 concentration or the inorganic carbon concentration in the ocean based on its isotopic signature. So fossil fuels have more carbon-12 in them relative to the natural abundance of those, the isotopes of carbon, and so by looking at the ratio of carbon-12 to carbon-13 in the inorganic carbon in the ocean, we can tell how much of it is anthropogenic. And you can see that the North Atlantic really sticks out as a place where anthropogenic carbon is going into the ocean, and that's because of deep water formation in the North Atlantic. So the Gulf Stream comes up here, it's warm, it's salty. When it cools around Labrador, it sinks efficiently and transports that anthropogenic carbon into the deep ocean. And also these mid-latitudes in the Southern Ocean where intermediate or mode waters are formed, so the subduction of water that was up or around Antarctica is also a place where anthropogenic CO2 is entering the oceans. Now, what impact does that have on the oceans? So here are long-term records from 3 ocean time series sites. The BATS in the sort of green colour here is the Bermuda Atlantic time series, so that's right here. Aloha is the Hawaii Ocean Time Series site in the North Pacific, and the STOC is the European Time Series site in the Canary Islands in the eastern North Atlantic there. So what's plotted here, the colours are the different locations, and the 3 plots are different CO2 species or impacts in the ocean. So we can see that as atmospheric CO2 increases in the black line there, the concentration, the partial pressure of CO2 in the surface waters is also increasing because the oceans are taking up some of that CO2. This decreases the pH, so I think you're all aware of the idea of ocean acidification. So what happens when there's more CO2 in the atmosphere, some of that goes into the ocean and it reacts with seawater to form a weak acid basically. And so that is decreasing pH or increasing the acidity of the ocean. And the amount is quite small in numerically, but pH is a log scale. It's the negative log of the hydrogen ion concentration in water. And so a very small change in the numerical value of pH is actually a very large change in the percentage value of pH. The other thing I want to point out is that we all know that neutral pH is 7, and the oceans are not acidic yet. They're alkaline or basic, and so when we use the term ocean acidification, it's not that the oceans are acidic or they're becoming a stronger acid. They're tending towards becoming an acid, which doesn't actually, whether they're an acid or not, doesn't really matter for the biology, and I'll touch on that in a minute. Or how about right now? So one of the impacts, yes, as pH decreases, the plants and animals that live in the ocean are feeling it more like an acid. But perhaps what's more pressing for them is the concentration of ions that they use for performing things like calcification. So phytoplankton and higher organisms that have calcium carbonate shells, the equilibrium of CO2 in the ocean is such that when you dissolve more CO2 in the ocean, you get lower concentrations of carbonate ions, and that's what these plots are all showing. And that's a problem for plants and animals that make in calcium carbonate shells because they have less of this carbonate to do that with. And so this is explained on this next slide. So this is illustrating a couple of things. First, it's illustrating the equilibrium that occurs between the different species of carbon in the ocean. So there's the three main things that make up carbon in the ocean are bicarbonate ions, which account for about 90% of the carbon in the ocean, carbonate ions, which is about 9%, and aqueous or dissolved CO2, which is about 1% of the CO2 in the ocean. And there's equilibria reactions that go on between these species. And so the net effect of dissolving more CO2 into the ocean is that the concentration of dissolved CO2 increases a bit by, in this case, by about 10%. The increase of the concentration of bicarbonate also increases by about 10%, and the total amount of dissolved inorganic carbon increases by only about 1%. But you see that this also leads to a decrease in the concentration of carbonate ions, and that's what's shown here, and that's what's a problem for biology. We can quantify the ability of the ocean to take up CO2, or the buffering capacity of the ocean, by what's called the Revelle factor. So this is named after Roger Revelle, who was a chemist at Scripps, who also has a ship named after him. So what it is it's basically the relative increase in CO2 that you observe for a relative to a relative increase in dissolved inorganic carbon. And so in this example here, where we increase CO2 by 10% from 350, the Revelle factor is about 10. And so what that means is that CO2 increases about 10 times the what the dissolved inorganic carbon. Sorry, I should have said dissolved inorganic carbon is basically the sum of all these. It's all of the inorganic carbon species in the ocean. Now, so what this means is that short story is that as you dissolve more CO2 in the oceans, it becomes harder to dissolve more CO2 into the oceans. So that has an impact on what the CO2 sink is going to do into the future. So if we map the Revelle factor, and a higher number means harder to dissolve CO2 into the oceans, and if we map the Revelle factor, we can already see high values in some high latitude locations. So as atmospheric CO2 increases, the carbonate ions in the ocean decrease, and the amount of uptake also decreases. So that carbonate ion problem can be quantified by what's called the saturation state of aragonite or calcite. So aragonite and calcite are just two different forms of calcium carbonate in the ocean, and they're synthesised, or they're made by phytoplankton, other calcifying organisms like pteropods and mussels and oysters and things like that, and corals. So what this plot shows is how much those plants and animals how well they can calcify as a function of this aragonite saturation. And the scale here is backwards, but what it basically shows is as the saturation gets lower, below about 2, it's hard for corals, in this case, to calcify. And if we look at the current present-day distribution of corals in the ocean, they are mostly residing in waters that have relatively high aragonite saturation states. But as the oceans acidify, so here's scenarios for different, well, here's where we are now, right, 400 ppm. As we go to increasing CO2 concentrations in the atmosphere, the distribution of the aragonite saturation moves towards 0, which means it's going to be harder for corals, for instance, tropical corals, to make a living. And the truth is they're probably buggered before then because of warming, but anyway. So that's the future for corals, but this is already a problem in coastal areas. So here's some data from the west coast of the US, and this is showing the depth of the aragonite saturation horizon, so where aragonite saturation is 1 as a function of latitude along the US west coast. And so if we just zoom in on one of these sections, so here we are in Oregon, going from the coast offshore, and this thicker line here is 1. That's the Aragonite saturation of 1. So anything below 1 is definitely difficult for calcifying animals, plants to synthesise Aragonite. And you can see that we have, so what you could refer to these as corrosive waters. So waters where it's very hard to make calcium carbonate coming right up to the surface. So, you know, when I lived and worked in Oregon, I had colleagues who were working on this problem. There's oyster hatcheries along the coast of the US West Coast, and so these are where you make baby oysters to ship off to oyster farms, and they're all dying when they're sucking in this water with Aragonite saturation of less than 1. So they put in place a mitigation mechanism. You know, they change the chemistry of the seawater that they're circulating, or they don't suck in water when upwelling is occurring. But the reason these iso lines of Aragonite saturation are bending out towards the surface is because of upwelling that happens along the coast of California, you know, mostly during the summer up here and all times of the year down here. So that's for, I'm not really going to talk, I mean there's massive amounts of literature that's coming out on the effect of acidification on mollusks and gastropods. What I'll talk about now is the effect on calcifying plankton. So on the left here is an image of representatives of a group of organisms that are called the coccolithophorids. So these are the calcifying phytoplankton. So they're phytoplankton, single cells with a calcium carbonate shell around the outside. The diatoms are somewhat similar, but they have a silica shell around the outside. And both of those are thought to be strong contributors to the biological pump of CO2 into the deep ocean because they form dense blooms that can sink out rapidly. Or as Barney Bolch from Maine likes to say, you know, when these things die, they sink like rocks because they basically are. They're little calcium carbonate rocks. So in the top panel here is 2 different species grown under normal conditions, and this is sort of one of the early seminal papers in the ocean acidification literature that then grew these phytoplankton at higher CO2 levels, and it was harder for them to synthesise calcium carbonate. You can see that visually in these malformed lids here, and here we can see it graphically in terms of this is their calcification rate. So how quickly they're making calcium carbonate as a function of, you know, CO2 concentration or carbonate ion concentration, or we can look at it here in terms of CO2 concentration. So what this shows is that CO2 concentration increases, the carbonate ion concentration is decreasing. And so this is back in 2000 when atmospheric CO2 wasn't 400 yet, but they grew their phytoplankton at pre-industrial, current day and future scenario CO2 concentration. So you can see this value here of 700 and something corresponds to, you know, where we might be towards the end of this century based on different RCPs. And so these phytoplankton calcify less when the ocean is acidified. So if you look at how atmospheric CO2 concentrations have changed between glacial and interglacial periods, there's a lot of work on this, and perhaps that's going to be talked about in the paleo lecture to come. But I think it's fair to say that the current thinking is that probably no more than half of the changes of the 100 ppm change in atmospheric CO2 that we saw between glacial and interglacial cycles was due to ocean biology, so that the biological carbon pump capturing CO2 at the surface due to photosynthesis and storing it in the deep ocean. The other half was due to other physical processes like ocean circulation. So if these guys are a significant part of the ocean sink, and if it's harder for them to make a living into the future, that's going to have implications for the magnitude of the ocean sink. And which brings me to the last slide here. So this, I put this paper, or Melissa put this paper up on the website. I should have mentioned the other paper that is up on the website is a paper by Chris Sabine that explains the anthropogenic CO2 going into the ocean. So the slide I showed with the anthropogenic signal in the ocean is related to that paper. So this is a paper by Rockstrom and others that was in Science earlier this year, and it shows how we might meet the Paris goals. There's a lot of information on this slide, so I will go through it in a couple of steps. So what we've got here is time on the x-axis going up to 2100, which is where we want to either, in this case here, limit global warming below 1.5 degrees at 50% probability, or below 2 degrees at 66% probability. This axis here is emissions per year, and this axis here is cumulative emissions. So there's a couple of things to point out here. So they say that basically starting now, we have to halve our emissions every decade. And that's what this black line is here, halving our emissions every decade. And then these shaded bars here, you have to look on this axis over here, is the accumulation of those emissions in the atmosphere. So this is how the emissions accumulate, and they plateau there because they're plateauing here. So to basically get emissions down to, emissions down to about 5 gigatons per year by 2050, which with the changes in the sinks means net emissions of 0 by 2050. So to do that, the CCS, carbon capture and storage, has to increase, so we need to instigate mechanisms to capture CO2 out of the atmosphere, and we also need to change land use in the other direction to start capturing CO2. So the sinks increase, that's the these two colours here, the orange and the yellow. And so the impact that they have on the land use change source is that they turn them from a source to a sink in around about 2050. So you see that in dark here is the land use change source, and it disappears by 2050 because it's compensated for by the yellow bar there. But there's also, so this is based on a model, and you can read the paper for the details of the model. But they also do take account of the land and the ocean sinks changing. So two of the ways that we think the ocean sink might change is, as the ocean warms up, it's harder to dissolve CO2 in warmer water, so that's one process that's physically going to limit the amount of CO2 that can go into the ocean. Also, a warming ocean might be more stratified, and so that's going to reduce exchange between the upper ocean and the deeper ocean, so it's harder to get the CO2 into the deep ocean. The biological sinks might change in ways that we don't properly understand, but some of the emerging consensuses are that, as the ocean warms, if the ocean warms and becomes more stratified, it might be harder to get nutrients into the surface waters by seasonal mixing or by upwelling, so that's going to reduce ocean productivity. If acidification has a significant impact on ocean productivity by impacting the calcifiers that I talked about, then that might reduce the size of the biological pump. So you can see that this blue wedge here becomes smaller as time goes on because the ocean sink is becoming smaller. And then the land use, the terrestrial fires here seem to go through a period of contraction and then expansion. I'm not sure of the details on that one. Now this is the part that Steve talked about a little bit. This is how fast are renewables going to increase. So right now, the amount of renewables is doubling about every 5 years. So if that continues, that's this line here, where we'll be at 100% renewables by about 2040 something. Coal will be totally gone by 2035, and oil will be totally gone by about 2045. But you'll see that they've also got some other scenarios here where there's either a linear increase in the annual gains, or there's just a constant increase in the annual gains. So this is doubling at the rate that it is right now. And then this plot here is just basically again showing the same one here. This is a reduction in emissions, emissions halving every year. So this gives you an idea of how dramatic, not only in fossil fuel reductions, but also in terms of capture and storage and land use change, the scenarios need to be to get to the Paris goal. And you can read the paper that's on the website. Okay, so to summarise what I've talked about, emissions are increasing. We seem to be tracking RCP at 8.5, and depending on your point of view, you could call that worst case scenario or business as usual. Per capita, emissions are stabilising, and the intensity is definitely decreasing, so economies are becoming more efficient in terms of fossil fuel use. There's interannual variability in the atmospheric accumulation, and we can see that that's driven by two things: the climate modes of variability, so that was the effect of El Nino events in Indonesia and on the equatorial upwelling source, and also economics. So we saw the impacts in the atmospheric accumulation due to various economic crises. The sinks are, to some extent, keeping track with the emissions, but we don't know how long that will continue for, especially for the ocean. And acidification of the ocean is already impacting some ecosystems. So I showed the example from the California upwelling system, and perhaps impacts on corals to come. And finally, rapid decarbonisation of the economy to meet the Paris goals requires drastic and immediate action. And on that positive note, I will end and take any questions. Yes.
I was wondering if you heard if any kinds of biology in the ocean actually respond positively to pH decrease.
Yeah, good point actually. So yeah, just in China, and also a couple of weeks ago I gave an ocean acidification lecture to the classes there, and yeah, I mean the early results from the ocean acidification work was exactly what we expected. You change the pH of the water that these calcifiers are grown in, and it has a negative impact. Since then, there's been a lot of other studies, and the results are a bit more nuanced, and that's a polite way of saying that they're contradicting each other. So what it seems is that, yeah, there are, for phytoplankton, but also for higher animals, there are species that respond positively and species that respond negatively to ocean acidification. And a good example from just one study that I've seen is that nitrogen fixes, so trichodesmium, seems to have a positive response to ocean acidification.
Is that just because of acidification, or is that because of the stratification that's associated with
in that particular one, it was just acidification, because it was just a chemical manipulation of the phytoplankton.
Okay.
But yeah, so yeah, I said before that stratification could decrease the nutrient exchange between the deep ocean and the surface waters, which could decrease ocean productivity. But for instance, results from that Hawaii Ocean Time Series site suggest that, you know, since the 60s, when the ocean has warmed and there's been more and stronger El Nino events, that stratification has increased in the North Pacific subtropical gyre, and that's favoured these cyanobacteria that can fix nitrogen out of the atmosphere, and it's actually increased the surface nutrient concentrations in that part of the ocean. So yeah, they're all competing feedbacks. Yeah.
So when you look at GDP and CO2 emissions, efficiency is increasing. Does that affect inflation or is that?
That's a good point. I think the GDP is probably adjusted for inflation. Yeah, I think it would. Yeah.
I was wondering, what kind of residence times do you see for anthropogenic carbon in the ocean?
Yeah, that's a good question. So part of the problem for climate change is not so much the CO2 concentration, but the rate at which it's increasing. And so, you know, people say, oh, you know, we've had high CO2 in the atmosphere before. What's the big deal? And yeah, that's true, but not in the last million years or several million years. And yeah, what's a bigger problem is how rapidly the CO2 is increasing. And in fact, so Steve showed one plot like this, and last year there was a Oceans in a High CO2 World meeting in Hobart, and Richard Seavey from Hawaii gave a talk where he said that, you know, the last time that CO2 increased as fast as it is right now was 65 million years ago, and that's when 3/4 of Earth's species went extinct. So part of the problem is the rate at which it's increasing, which is related to the residence time and the circulation time scale of the ocean. So the oceans, you can think of the oceans overturning on a time scale of about 1,000 years. If the rate of CO2 increase were a lot slower, the oceans would be able to compensate a lot more than they already are. But the timescales are too different right now. And so that also has implications though for it's not talked about so much anymore, but storage of CO2, like direct injection of CO2 deep into the ocean, was talked about for a while as a carbon capture and storage mechanism, and that's that may be feasible, but it might just create a problem that will come back in 1,000 years when those waters are at the surface again. So as this water gets into the CO2 gets into the deep ocean, it's also going to come up again sometime later.
So usually about 1,000 years.
So the residence time of conservative species in the ocean is about 1,000 years.
What do you think are feasible methods of carbon capture and storage going into the future?
Yeah, okay, so one thing that I have some expertise in is iron fertilisation of the ocean. So, when that was first talked about by John Martin, the chemical oceanographer from California in the 90s, he's famous or infamous for saying, give me half a tanker of iron and I'll give you an ice age. So he calculated a classic sort of back-of-the-envelope calculation. He said that with a couple 100,000 tonnes of iron, if you fertilise the Southern Ocean, which is also iron limited, you could draw down a couple billion tonnes of CO2 and reverse the effects of fossil fuel emissions. So since 1993, there's been about a dozen large-scale ocean experiments that have, some of them authorised, some not, that have put iron into the ocean and measured the biological and the biogeochemical effects. And in just about every case, the amount of CO2 that's actually exported into the deep ocean, so the particulate flux of any biology that's created into the deep ocean, is much less than John Martin originally calculated. And so it's still talked about, iron fertilisation is still talked about in terms of maybe transacting carbon credits, or maybe more recently in terms of stimulating fisheries. But my own personal opinion is that if it were to be done on a scale that would impact climate, it would have a lot of other impacts on the ocean that we don't fully understand and probably negative. I mean, my personal opinion is, as time goes on, is that I think we're going to end up having to monkey around with the atmosphere in other ways. We're never going to. Are we going to really get to zero emissions by 2050? I mean, do you think that the people who in the coal and gas industry want to see this number here? So I just think more and more that we're going to MacGyver ourselves out of this situation by solar radiation management or something like that into the future. So that answers part of your question. I don't know about other carbon capture strategies. So there's things like, well, first if you don't capture the CO2 at its source, you have to have some mechanism to concentrate it before you sequester it, and there are things that are talked about for that. Or sequestering at its source, so at coal-fired power station or something like that.
Just quickly, where are these figures from?
So this is this plot is directly from a paper that was in Science earlier this year that's on the website, and the actual numbers are from a climate model that they described in the paper.
Do you remember what's the author?
Rockstrom. Rockstrom is the first author, Rockstrom.
We'll just go to the supplementary material page of the website.
What is that? Sorry.
Yeah.
How does the long-term climate variability will affect the carbon sequestration in the ocean, like IPO or the hydrous event?
Yeah, good point. So, well, the IPO is sort of like a long-lasting El Nino, I would say. So I mean, it's linked. It would have a similar. I guess the IPO influences El Nino, which then influences the whatever El Nino does to the sinks, like reducing the equatorial source.
There are two different cases where the IPO lasts long, but in the present scenario, it is like the El Nino is increasing in the intensity rather than frequency.
Yeah. Okay. Yeah.
But the IPO is still negative.
Okay. Yeah. So if the IPO increases the intensity of El Nino events, it will.
Yeah, but because we are getting much more intense, and whether while we are having a negative IPO state also.
Oh, okay.
So how does it will affect the sequestration of carbon into the ocean?
Yeah, I guess I don't know the answer to that. So, yeah. I don't specifically know much about direct links between the IPO and the sinks. Okay, let's serve it.
Thank you.
Okay.